We are now going to use libraries that are included with the R programming language, which are able to do random forests and gradient boosting directly. So we're not going to use code that we have cobbled together to mimic random forest. In fact, all you need to do is load in random forest. For gradient boosting, we're going to use a library called GBM. Now you'll notice I put a little comment up here that this is not, there are other gradient boosting libraries that are available. This is not necessarily the best one. Probably the most popular one is called XGBoost, but this one is selected because it is a very simple one, and if you are just getting started with gradient boosting in the R programming language, you probably are going to want to use this one. It's simple. It's perfectly fine. It's going to give you some excellent results, but just know that as you become more skilled with R, you may wish to explore different libraries which can do gradient boosting. So we're going to load in the libraries, and we're going to load in our data set that we have been using up till now. And this is the insurance data set, and we're going to try to use this to predict who's going to crash their car. And let's get the data set together. We're going to split it into a 70-30 split. 70% of our data will be for training, and the rest will be used for testing. So let's do that. And you can see here we've got 46 variables. One of these is the target. We've got a total of 10,000 records. We're going to use 7,100 for training, 3,100 for testing. So we will start off with our friend, the decision tree. And this is going to yield a decision tree that should look familiar from other videos. And we will, in fact, we've predicted here. We've got the decision tree model here, and we've predicted and we've created it. And now we're going to predict using our decision tree. We're going to use our test data set, and we're going to predict this probability. So this is the command, and we've done that already. And now we're ready to use that for comparison. But first, we have to build a random forest model. So we are going to use this command right here, and we're going to build 500 random forest decision trees. And let us run that thing, and let's take a look at the clock. It's 3:39 right here. So this is going to take a couple of minutes, and I may pause in a moment, but some things that you are going to want to consider for the R programming or for random forest. You may wish to set importance to true. And the purpose of that is we're going to want to ask R after we're done to tell us which variables are the most important in determining who's going to crash their car. So that's always a smart thing to do. Also, we are just going to tell R that this is a regression tree. So because our target is a 1 or a 0, we can tell R, hey, listen, this is a regression, and we don't have to tell it it's a class variable or anything like that. This is perfectly fine. However, R may give us a warning message saying, hey, listen, if this is a regression, why do you only have two values, 1 and 0? Doesn't matter. We know what we're doing. So that won't be a problem. But if you see a message like that, please do not be concerned. With that in mind, I'm going to pause this video for a moment, and so you don't have the awkward silence as we wait for R to complete building a random forest. And we are back, and here it's 3:41, so it just took a couple of minutes, but this is going to take considerably longer than gradient boosting. We will take a quick look to see how important the variables are. So let's take a look there. And R will give us two different columns here. One is for a percentage of increase in the mean squared error, and also the node purity. So there's two different ways the random forest can tell us which variables are important. These numbers are certainly useful, but R will also give us a variable importance plot, which is very nice, and I think can be very useful. And when you just visually look at this, depending on the metric you use, you can see, for example, that whether or not you live in the city or the country seems to be a very important variable from this perspective. And if we look down here, it's still important on this chart as well. So it seems to be a very important one. Some other ones, Blue Book, travel time to work, have you filed claims in the past, things like that. These are all making sense. So if I were to do use this for variable selection, I might just take this group right here and use them. So anyways, we've got a random forest that has been developed. Let's predict we're going to throw the test data set in here, and we're going to predict that. And we've now used the predict command, and we're ready to go for the random forest. Now we just have one more to do, and that's the gradient boosting. So with the gradient boosting in GBM, we need to tell R that if it's a 1 and a 0, we have to use this argument here, distribution Bernoulli. And we're going to again use 500 decision trees. Now let's look at how fast that one is. It took like 2 or 3 minutes for the random forest, but this gradient boosting algorithm is quite fast. And we are almost done. Yep, we're done. So that only took a few seconds. Obviously, it took more time than a decision tree, but it still was pretty fast. Now, gradient boosting, the GBM model, doesn't give us a really nice, pretty plot like the random forest does. It gives us something that is actually less useful, but we can still glean some information. Summary GBM is the command to give us variable importance. Here's our model, GB model, and we're going to say C bars 10. And there it is. Now the reason why this is not such an important model here, or this is not a useful chart, is because I don't really know what all of these bars are. They're not all labeled. I can look here instead, urban, oldest claim, imputed home value, age, etc. So these are the variables, and I could just maybe take the first 10 here and count the first 10 here and know, but this is not, in my opinion, a useful chart. This is more useful for gradient boosting. And let us now come over here, and we will predict. Now, one thing you're going to do is when you do a predict with the gradient boosting and you're using GBM, you have to say, here's my model, here's my test data set. You have to say type equals response. If you don't do that, it's not going to give you any usable results. So let's do that. And there we go. Now, let us do a ROC curve to see how accurate these are. So let's start by just looking at the decision tree itself. This is just the vanilla decision tree that we've been using all along. And that's a pretty good model. But how did the random forest and how did the gradient boosting do? So let's copy those guys on top. And you can see both of them, the random forest is in red and the gradient boosting is in blue. You can see both of them were significantly better than just a simple vanilla decision tree. You're going to find that in many cases when you have a very complicated model, a large data set with many variables, these guys, the random forest and gradient boosting, will traditionally outperform a decision tree. Decision tree is faster, you can interpret it, it's easy to put into production, but these guys are more accurate. Usually, for a very simple data set, that might not be the case, but this is always worth doing. Now you can see that the gradient boosting with this data set has been consistently outperforming the random forest. That is not always going to be the case. Different data set, different problems. Sometimes random forest is better. Try them both. And now let us see how the area under the ROC curve is. So we do that, and you can see that the decision tree gives us a 72% area under the ROC curve, very respectable, but our random forest gives us 81, and the gradient boosting gives us 81 and a little bit more. So they both are about the same, but the gradient boosting was faster to train. So anyways, this is using random forest and gradient boosting to predict a probability. Now in the next video, we're going to use random forest and gradient boosting to compute the amount.